So it now gives me great pleasure. We'll move on to the main part of the evening, and it's great to have so many of you with us here tonight. I'd like to introduce Tony, who's going to speak to us about the Hubble Space Telescope. So, Tony, the floor is yours, as they say.
Right, fine. Let me just go into screen share. It'll take me a few minutes to get to the correct point. Share screen. We have to put the sound on it. If anybody's on earphones like I am, at one point you might think of just half taking them off. The one bit does get a little bit loud. Here we go, share. Hopefully we're getting there now. Where are we? Onto the full size. Sorry. Slideshow on the current slide. Gosh, it takes a long time. There we go. So just minimize down a little bit. We'll do it. There we are. Right. Well, thanks very much for inviting me, Darren and Plympton Rotary Club. It's a delight to come down. David and myself have been whizzing around the country quite a lot. It's about 25, I think, now. Quite a lot up in Scotland, but I think this is the most international group that we've had, so it's a real delight. I did a talk on Hubble for my own club about probably in July of last year, and it went down reasonably well with them, and finally we thought it might go down reasonably with the Rotary International in Great Britain and Ireland, and so it's on their site, and this is where things have come up. It's really dedicated to the end polio now system. I've been a great believer in this, and it's been going for 40 years. And we're getting there, very, very nearly there. But all the way along, I've said never charge for this talk at all. But if any of the clubs are happy enough and they want to pop any pennies into the End Polio Now scheme on behalf of this talk, then it'd be a delight. So no more, let's go over to starting it then. And as I say, it's a delight to come across or down to Plympton from snowy Glossop. We had snow, I think it was yesterday, David will confirm that. If I can bring my greetings from President Rotarian David Phillips and all the members of Glossop Rotary. So let's, with no more ado, move over and start looking. Seems a long way to go back to the 17th century, but it's a good place to start, I think. We've got Galileo Galilei. He was an Italian, absolutely incredible brain. He was an astronomer, a mathematician, physicist, and engineer. He didn't discover the telescope, but he certainly improved and made phenomenal discoveries with his improved telescope. As such, he became described really as the father of astronomy. He discovered Saturn's rings, the moons of Jupiter, and sunspots. Unfortunately, or fortunately for us, whichever way you want to look at it, the Roman Catholic Church he fell out very badly with because he was teaching heliocentrism, which is completely opposite what the Roman Catholic Church was teaching at the time. And they believed in the geocentrism being the fact that Earth is the center of the universe and everything goes around Earth. What else could it be? Of course, Galileo was talking about heliocentrism, which said, no, Earth is a planet. We all go around the sun, and there are planets and moons going around different areas of it. He was publishing a lot of papers at the time, and he published one paper which really went down terribly badly with the Pope and some of his senior cardinals. As such, he was called to trial on a charge of heresy, a very, very serious charge indeed. Goodness knows what would have happened to him if he'd been not befriended by 2 or 3 cardinals. And you can see a couple here looking at, one looking through his telescope, and the other looking very, very skeptically at some diagrams he has describing some of the planets, and I think he's got Mars and Jupiter there. He went to trial, and his friends in the Roman Catholic Church said, whatever you do, plead guilty, and that's the only way you will get out of this. And on their advice, he did plead guilty to the charges of heresy, and the sentence was quite a lenient one in those days, and it was one where he was plonked into indefinite house imprisonment. So for the rest of his life, it was about another 15 years after he faced the charges, he was locked away in his own house, but that didn't stop him publishing papers and things like that. So, certainly at the forefront of engineering and astronomy. Jumping forward now into the 20th century, we've got a gentleman here called Edwin Hubble. Obviously, his name was allocated to the Hubble telescope. And here you can see him with a rather massive different telescope. It's a reflecting telescope rather than the refracting telescope that Galileo was using. And this one, quite a huge diameter, huge bearings and mountings and all the equipment to it. But when it comes down to it, the image is projected down at this bottom corner here into about 1 1/4 inch diameter lens, the eyepiece. So everything there brings in a lot of light, hopefully, and information. Hubble was very, very prominent in the fact that he postulated that there wasn't just one galaxy. There were, in fact, hundreds and thousands, he predicted. But what he did also predict was the fact that these galaxies aren't stationary, they are accelerating away from us. So the whole of the universe, as he was watching it, is accelerating away. And he introduced something which was called the Hubble Constant, which is a factor which helps calculate the speed of movement in the stars and the galaxies. And it's still used today. What would he have said if he could do something like that? Here we are, he was in the mid-30s. Here we are in the very late 50s, early 60s with a telescope. It's called the Einstein Telescope. You can see all the solar panels on it. And this one is really looking at, in the X-ray spectrum. It wasn't terribly much in the visible spectrum, but it was a start, and we'll see later one of the discoveries it made was quite extraordinary. Wouldn't Hubble, Galileo been pleased to have seen this? Here it is, the Space Telescope Hubble, and we'll not go into much detail here, but if we just look at it, the Earth's surface, I think it's somewhere over the Chile coast, I'm not absolutely certain. But if we look at the Earth's surface here, you can see the ionosphere and the Earth's atmosphere. And that is a real problem to Earth astronomers. It really has lots of dust and dirt in it, vibration and movement. And it's only on very, very good days that you can get good, clear pictures when the sky is still. You've probably seen it yourself when you look up into the stars and you can see it's a beautiful, clear night. The best place for viewing on Earth is high up on mountains, and there are telescopes in Spain, in the Chilean mountains, the Andes, and in Australia. So these are high up and they get good pictures. But this is Hubble, just to give you an idea what it is. There's a lot of proposals that we should build a telescope, and it's obviously NASA who was very active in this area. And it was in 1969 they accepted the concept of constructing and launching a very large space telescope, later named Hubble after Edwin Hubble in honor of his discoveries. Congress approved funding, and they said it would launch in about 1983 using the space shuttles, which were a good tried technology at that time. And the actual budget was given at $36 million. The European Space Agency joined the project later on, and there they improved the funding and also a lot of design expertise. Then the problems started to develop. The mirror, the big primary mirror, which we'll look at and see how that works, it caused significant delays to the project and pushed the launch date back to September 95. And then in early 1986, we had the Challenger launch disaster, where there was that dreadful explosion of the Saturn rocket, which killed think it's 5 of the astronauts. It was absolutely horrible. But of course, that knocked things back. It knocked Hubble's plans back by another 4 years, and the budget now was rising steadily. And instead of the 360 million, it was now up to 4.7 billion. The mirror itself, the primary mirror, was reduced from 3 meters down to 2.4 meters. And finally, using the Space Shuttle Discovery, it was launched on April 24th, 1990, very nearly 30 years ago. The orbits were somewhere around 550 kilometers above the Earth, and the orbits take somewhere around 97 million minutes with a speed of 28,000 kilometers an hour. So if we look at the simple design of how it works, when you're looking at a distant object, the light is coming in parallel, and the light comes in on this top and the bottom path, and it hits the primary mirror here, which is the parabolic design. And the properties of parabolic design is any light coming in, it hits the mirror and it focuses down to a point. So it bounces off the mirror, coming up to the forward, it would go straight outside if there wasn't a secondary mirror here, supported down here, and that bounces it back, the light, through a big hole in the center of the primary mirror and onto the charge coupled devices, the optics in the back over here. The light is governed by an aperture here. The aperture door opens, and we'll see that in a short while. So it gives you a rough idea. Let's have a look at this mirror. You all know there were serious problems on the Hubble mirror. And here it is, precision grounding. And it was one of the most accurately ground devices of its time. Absolutely incredibly well done. And here's one of the engineers looking over it with his tie hanging loose. He wouldn't get away with that nowadays. But if we look later on, here they are, measuring on it, checking to see the surface and everything. And it all looked good. The diameter, if this diameter is 2.4 meters, if it was blown up to represent the diameter of Earth, it's reputed that the irregularities on the surface, the bumps and humps here, will be no more than 6 inches high. Perhaps takes a little bit of believing that, but that's what they say. The big problem that nobody knew about was out in these outer edges here. And it was overground by something like 2/50th the diameter of a human hair, or about 40 micrometers, that kind of order. But nobody knew about it, so everything went ahead. There were an awful lot of problems grounding it. You'll see in the center here, here's the hole where the light comes through from the secondary mirror, bounces off the primary, onto the secondary, and through the center here to the optics. Here's the finished job. Somebody looking at it, quite amazing picture. There's a cap on the actual centerpiece here, but here it is, virtually ready to be assembled into Hubble itself. If we look at simple engineering of it, and it is a mighty fearsome device, it weighs about 10.5 tons, and it's the size of a school bus or a 54-seater coach, that kind of order. So it's very big and it's very heavy. The aperture door at the front opens. It shuts when Hubble's moving anywhere within, I think it's about 20 degrees of the sun, so it doesn't let masses of heat in and burn out the electronics. Light comes in again, down the tube, hits the primary mirror, bounces off it, onto the secondary mirror, and the secondary mirror here is supported by 4 what we call spiders, and we'll see those on some of the photographs. The light off the primary mirror, onto the secondary mirror, and then straight through down into all the optical electronics down at this back end here. It's driven and moved primarily by electric motors, which we'll explain. But a lot of people say, why don't they use the same kind of thing as they use on most space rockets and everything, satellites? Burn a bit of fuel through a little nozzle, and to action and reaction, Newton's laws. Then if a nozzle squirts a gas out in one direction, then the body will tend to move the other direction. You can't do that with Hubble. For one thing, you'd never be able to store enough gas, with it being about 30 years old now. But the other thing is that if you were burning a gas and throwing it out, it could very well drift and cause a serious problem with the light coming in. So how do we move it? It's fairly simple. We have here some things called reaction wheels. And if you like to think of them, they're a bit like a gyroscopic wheel driven by a motor, quite large, quite heavy. The motor spins them up. And if it's spinning something, let's say it's going clockwise in that direction, it's spinning clockwise, then the motor mounts and everything obviously tend to move in the opposite direction. So if it's going that way, the body of the motor will tend to move that direction. And so we get a movement in that direction. If we put another of these reaction wheels here and have that spinning whichever direction, if it's spinning anti-clockwise, let's say, going there at right angles to that one, then Hubble will tend to move in that direction. So we have the basic concept of movement by electric motors. The electric motors, they're driven by batteries, fairly significant long life batteries, obviously. And they're kept charged by the solar panels, the solar arrays, two of them either side. And you can actually see them when you see the International Space Station going over you late at night or, well, sorry, just after dusk or early morning. These solar panels collect the light energy, and their capacity is about 5 kilowatts. So it's quite powerful and brings in a lot of light. And obviously, it's coming more directly from the sun, so it's pretty good. That's 5 kilowatts is taken over to the batteries here. And the batteries themselves are generally supplying usually a maximum of about 2.7 kilowatts. So there's quite a bit of reserve there. And basically, that's how Hubble is steered and how it is powered. All the cameras are at the back, quite an array of them working through different spectrums and different analysis. The computers in the Hubble, they were, well, if you look at them compared to a modern day telephone, they're pretty primitive, but they have been updated. They don't do masses of photographic processing or anything like that. What they do is they take the information from the cameras themselves, which has been digitized, and they feed it, collect it, and then it's sent up to some pretty high gain antennas. There's one there, one pointing the other way there. And that sends it by a route, which we'll look at in a second, back down to Earth, where it's processed. So that's the basic concept, a big heavy item floating around almost zero gravity. And if we look in the focal plane, we've come primary mirror, secondary mirror, through the hole in the primary mirror. And this is the focal plane of the actual camera of Hubble itself. Around the outside of it are some field guidance sensors. There's 3 major cameras here, and they in turn are responsible for holding Hubble on a distant target and holding it steady. If you're doing photography, the last thing is you don't want wobble or anything like that. What they tend to do is to look at some fairly bright star, something that's in the field of view, and look at that. Now, if Hubble starts to drift, say it's drifting this way, something like that, then these cameras actually, the sensors, detect this drift and say, well, that's no good if we're doing photography. Then what they do is wind up the reaction wheels so that they go back to the original position. So the image is kept in a very, very tight field of frame. And it's something like if Hubble's looking at a human hair 10 miles away, something like that, then it can hold its position on that for about 10 minutes, which is quite a remarkable point that it can hold and lock in, because they do a lot of exposures, and some of them are quite long exposures. Major cameras around here, wide field camera, the COS, which is the Cosmic Origins spectrograph, imaging spectrographs. If we had time, we could look inside all these and see what they do. Fairly primitive in the 1990s, again, compared to modern Samsung or an Apple phone, but we'll see how they bring the pictures up before too long. assembly of Hubble. Here it goes. The engineers are working on it, getting it near ready. And here it is, very nearly ready for launch. You can see the aperture door here, and you can see masses of foil and aluminium insulation there. And the idea is this, is to try and keep the temperature within Hubble constant. And it's somewhere in between 22 to 24 degrees centigrade constant. If it was actually rising up and down as Hubble goes through daylight and then around the back of the Earth into darkness, then it would have a pretty drastic effect on the mirrors and the focusing equipment. So they keep the temperature fairly constant inside. Here you can see one of the solar panels. They are flexible and they're on like a roller blind, and we'll see that in action later on. So it is ready to go into the back of Hubble. So a little bit of a poem I made up. Hubble, Hubble, toil and trouble, dollars to find and mirrors to grind. Nickels and dimes will set the times. Problems galore will it ever soar? Many say no, 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 but more say yo, yo, yo. 4, 3, 2, 1. Discovery, you're all set to go.
Start.
25.
Booster hydraulic power units have started.
20.
Sound suppression water system has started.
15.
Minus 13 seconds.
10.
T minus 10. Go for main engine start. We are go for main engine start. T minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Mission Control, Houston.
Roll program. Roger, roll, Discovery.
The roll maneuver puts the vehicle in the proper launch plane.
Start.
Well, there we have it. Hubble's off on its journeys. So what we have here is one of the women astronauts on the first launch of Hubble. She's called Dr. Cathy Sullivan. Again, an absolutely magic brain, physical capacity, calm under any situation. And she at the moment here is looking at the launch of Hubble, getting everything. You see she's got a pair of binoculars in her hands and she's looking out through one of the windows whilst Hubble's being launched. And here it is. We're looking at the front of the actual space telescope. Telescope is here, obviously. Inside the cargo bay of the Shuttle Discovery itself, there's a large control arm, and this robotic arm brought Hubble out, lifted it up to a set point. Everything was checked, the roller blinds were released and the solar panels were actually unfurled, the aerials were attracted, and the aperture door here is shut. And it's rather a lovely photograph of this because you've got pictures of the, well, it's a reflection of perhaps one of the oceans, something like that, with some clouds, and obviously the sun here. And off she goes, floats away, and it's quite a sight actually. She's probably doing some of the first measurements here. How do we get information back? Well, before we look at any of the information, let's assume it's looking to a galaxy, a faraway galaxy. Light comes in all the way down to the cameras at the back. It's digitized from the cameras and collected, and then it's sent up by one of the aerials out to a tracking data relay satellites. There's quite a few of these following on a similar orbit to Hubble, and as Hubble passes the information to it, it then is amplified and sent down to Earth to the ground station in New Mexico, White Sands. And from there, it's beamed across digitally to Baltimore in Maryland, and then it goes into the Space Telescope and Science Institute. Here they collect all the data, play around with it, do lots of work on it, and hopefully at the end come out with a picture, something like that. And if they're good enough, it's then released to the general public or whoever asks for the actual photographic work to be done. The Space Telescope is an open access area here, and meaning that anybody can actually request the use of Hubble. If you want to look at a certain planet or star, something like this, then you can actually contact the Space Telescope Science Institute and request it. It's unlikely if you're asking for something fairly mundane, but on major observatories around the world and universities and astronomers, they put the bids in. The bids are shifted through by a committee. The ones that are accepted takes one perhaps and sends it down to the Goddard Space Flight Center, again nearby, and it then transmits that information required for Hubble, its position, the time of opening the doors, the exposures, which cameras, which filters they're using. So that information is collected here at the Space Flight Center. It's then shot out the opposite direction this time to the ground station at White Sands, up to the nearest tracking and data satellite to Hubble, sent across to Hubble, and it goes into Hubble's control system. And at the correct time, then Hubble guides itself onto the new target, and they hopefully take some photographs. So the first one's come up, everybody's delighted and really excited about it, and there it is. A blurred image of a galaxy M100. M is a Messier catalogue, but this is 100 in that catalogue, and it's an absolute nightmare. The reaction was terrible. $4.7 billion down the drain. The public were really infuriated about this. What a loss of interest and everything. NASA was condemned and trashed, particularly in the States, but also by its own scientists. They were so disheartened about it. Worldwide, there was enormous skepticism. But behind the scenes, between, gosh, my internet connection is playing up a little bit, so we'll carry on. Between 1990 and 1993, the engineers and scientists worked on the images that did come off Hubble, and they discovered that the mirror had been overground. Now, virtually everything on Hubble is designed to be replaced, but the mirrors and the secondary mirrors aren't. So they were a bit stuck as to what to do. It was quite a disaster. But some of the engineers and physicists came up with the idea that, well, you've got this aberration on the images. They know what it was and how it was caused, and managed to work that out. So what they did was put a new camera in. It's called a COSTAR camera. That stands for Corrective Optics Space Telescope Axial Replacement. Huge mouthful, but it's like everything else. They always try and find some abbreviation which sounds okay. But COSTAR was the name of it. And what this was, it was a camera behind a special set of lenses. And the light coming in from the whatever they were looking at was now fed through a series of lenses which put the negative effect in through the aberration. So if there was, say, minus 10 units of error there, the lenses went and put in, before it got to the camera, a plus 10 units. So the errors were supposedly cancelled out. This was the idea about it. And in 1993, December, the scientists put a new camera in. Here it's ready to be launched on the back of Atlantis. And let's just watch this.
Enjoy the ride, pal.
Nozzle check of the SRBs. Firing chain is armed. Sound suppression water system armed. T-minus 10, 9, 8, 7, 6, 5, 4,
bed. And his wife was bonkers, obviously. She's getting fed up of seeing that one, but I really do like it. And anyway, the Space Shuttle Atlantis is driven fairly close to Hubble, so much so it synchronizes with it, and its telescopic arm here, the robotic boom, comes out, grabs hold of Hubble, and brings it into a docking area, primarily at the back of the cargo bay. So this area comes down, latched in, and here we have another set of astronauts working on it. This is Cathy Sullivan working on it. And she's actually got the new camera, the CoStar camera here, which has its corrective optics. And she's going to put that into Hubble, and there you are. You can see standing on the end of the robotic arm, the doors, some of the doors are opened up on the actual back end of Hubble, and the old cameras are taken out, and this new CoStar unit is put in. And this is what it was designed to do. Any upgrades are supposed to be relatively easily done. You can say it's easily this, sending astronauts up and using the space shuttle. Here they are, another pair working. You can see how they're tethered at all times to parts of the actual shuttle itself, so that they don't float off into outer space. Newton's laws applied equally well here to every action as the equal and opposite reaction. So if they turn too tight on a spanner or something like that, they would just float off. So you can see they are tethered in. And here we are, ready to actually launch again. You can see the aerials, and here are the solar panels that are rolled in, so we can work on it. Here's the aperture door, secondary mirror about here, and the primary mirror in here, like that. And so they put new equipment in, and the idea of this is that the new equipment should hopefully correct the errors of the mirror grinding. There's another astronaut down here, and what men and women they are that went up there, cool as cucumbers. And here we are, first pictures. On the left, we've got the original, I think this is M101 now, another galaxy. And here you can see that rather significant improvement, they've cracked it. And of course, worldwide interest rebuilt in it, and to see these amazing pictures. And from now on, then the pictures were coming in thick and fast, and NASA and Hubble regained its kind of reputation, and everybody's keen to get these photographs. Let's look at some of the planets to start with. Here we have, obviously, Saturn, and beautiful picture. So perfect, you would think it's actually been drawn on a computer. But it's one of our gas planets, and here you can see at one of the polar areas, there's an aurora going on. You can't normally see those from the ground because of the angles we look at it, but here Hubble's got a perfect view of it. The ice rings around Saturn, and a truly amazing picture. Jupiter. Jupiter's another enormous gas giant, huge it is. All the time there's fiery explosions and everything going on the circuit, and you can see these storms, and pretty nasty. I think it's a very sulphurous atmosphere there. Well, it's not one that would want to go and explore or live on. Mars is obviously well and truly in our eyes at the moment. It's somewhere between 340 and 250 million miles away, whereas Jupiter was 360 odd miles away. So varying distances, but here we see Mars with a fairly big storm on it. And these storms occur very regularly. You've all heard the wind on Mars now, and from the last NASA Perseverance that landed on it, we could actually hear the wind blowing there. It's mainly iron oxide, rust on the surface, and here there's a pretty major storm, which was, I think 2018 this went on, and it lasted for about 3 or 4 months. Pretty serious because NASA had Perseverance, the Opportunity rover, and that was on there, and it wiped out the solar panels on that rover, and so that was the end of that mission. The new missions with Perseverance and all its incredible equipment on it, I'm sure that is very well protected against these storms. Here's an absolutely huge storm that was recorded, and I think that one was in 2019, and that one went on for months and months, absolutely enormous. You can see huge dust storm going on there. If we just have a look at some of the star maps, everybody's probably seen these, and you certainly know the Great Bear in the Northern Hemisphere, and Orion. This is the very famous one, Orion the Mighty Hunter. Here's his belt, here's his sword up here, arrows. Let's just look at two of the major stars on it. Betelgeuse, I think I've got a pronunciation there. It's an old star, it's huge, and it's dying. And as stars die, young ones are extremely bright, whitish coloured, and the redder they are, the older they are. This one is very prominent. You can actually see it red with the naked eye, especially if you look with binoculars. On the other side of it, this one is about 500 light years away. This side here, Regal, is 770 light years away. And he's been the sword area here at 2,000 light years away. What I'm just trying to show you is that there's no parallax here. Things are so distant that all we see is a kind of flat plane. And it does all alter over the millennia, but very, very slightly. So we see it, and we have the constellations as we know them. Before we leave Orion, down in this area is a nebula that we'll look at. It's called the Horsehead Nebula, and it's just down here. We'll refer to that later on. But, well, Hubble was watching this, but from Earth, you can even see this Betelgeuse was actually dimming and going dimmer and dimmer. And ground scientists thought, well, this is the end of the star, it's fading, but it was going so fast that Hubble was watching it, and this is what it saw. Here's the big red star itself, and here is a huge ejection from its surface, a plasma of dust and dirt, kicked out hundreds of thousands of miles into space. It condenses here and forms a whopping great dust cloud, a bit like stars when they explode, they go into huge clouds of dust. So here it is, it's coming out and it's forming the cloud of dust here. That dust cloud actually went across the surface of Betelgeuse, and it eventually cut out about 2/3 of the surface. And so from Earth, as we were looking at it from Earth, all we could see was the star, and we couldn't see this detail, obviously, Hubble could. And it actually showed us the effects of, everybody thought it was dying, but it wasn't. And I think it took about, it was sometime in early 2020 this occurred, and it took about 3 months before it cleared again and came back to its normal bright self. Interesting photograph, not of Hubble, it's a picture of Hubble in front of the sun, a lot of filters in front of this, and you can see 2 specks down here, blown up, there it is, there's a space shuttle, and it's actually in the process of going to service Hubble. So you can get incredible photographs both ways. Hubble can photograph the sun. I don't quite know how it does it. I expect it has a pinprick in the aperture door, and that's opened, and it lets enough light in without damaging things. Here you can see the sun has a great nuclear furnace, and it's a transit, this, we call it a transit, as a planet comes in front of it. It doesn't actually go close, but it travels in the line of sight between Earth and the star itself, the sun. And here it is, transit across the sun. On the right, you can almost feel the heat of this thing, is some of the coronary discharges. These discharges, huge masses of gas and dust and firing electromagnetic waves, come out hundreds and million miles away from the sun itself. And it gives a very, very impressive photograph. And these are the ones we can normally only see from Earth when we have a major sunspot, not sun, but a major eclipse. How do we get the photographs? Well, we all know that light splits into its component colours. There's blue, if you look at the rainbow, there's blue going into greens, into yellows, oranges, into the reds. This end is the high frequency end, the short wavelength light. This is the infrared, the top end of our eyesight here. This area here is lower frequencies and larger wavelengths. So to get an image, and this is Mars, it's Hubble's trained on it, and if we take this area here, what we do is put a green filter in front of the camera lens, and that green filter only allows green through and blocks off the blues and the reds. And they take a black and white photograph of the image with the green filter in front of it, and that's the image you get. Then they look at the same object and they put a red filter in front of it, and the red filter only lets the red light through, cutting off the blues and greens, and we get a black and white image then like that, different. And if we take a blue filter and put that in front of the lens, then we end up with a completely different image. And so we've got three images here, all taken through the filters. And what we do is then put the filters back in front of them electronically. They put a primary colours of blue, green and red. These are added to the black and white image of the blue filtered area, same with the green and same with the red. Those are then combined and bingo, this is what you get, a full colour picture. Very clever, and this is just some of the basic observational lenses and filters that are used. They use a lot more for getting different information out. Before we go any further, a bit of maths here, let's just look at distances and lights. The speed of light, it's enormous. It's 300,000 meters per second. That's a long, long way. Or 186,000 miles per second. Or in 1 hour, we've got this figure. Or in 1 year, if you scale everything up, it's going 9.5 million kilometers a year. Or in real terms, let's go over and have a look at it. 5 trillion miles per year. That is a long, long distance. So rather than talking about miles or kilometers, we can actually define things as being light years away. And this is a much more sensible term, because a light year now is 9.5 trillion kilometers or 5 trillion miles away. Now these numbers are huge, and it's worth bearing in mind that since Jesus Christ was born, there hasn't yet been 1 million days passed. And here we're talking millions, trillions of kilometers and miles. If you do the sums, you'll come out somewhere in between 0.75 and 0.8 days since Jesus Christ was born. So it's giving you an idea of the size of it. The sun's only 96 million miles away. It sounds a long way. And light takes 8 minutes to reach us. And therefore, a light year represents something like 52,000 million times distance further away than our sun. So we're talking big numbers. Enough of that. Right, if we now start looking away from planets and light and get a little bit more involved in the light year, here's a very, very lovely picture. It's our own Milky Way galaxy, the one that we're actually sat somewhere out at the edge of. And Hubble's looking into the Milky Way galaxy here. Noticeable point here is a huge mass, and it is a black hole, and it's got a density of about 4 million times that of our sun. Massive. Any light or particles or anything just come in and disappear into that black hole, and it's no good asking me what's going on there. There's a lot of research coming out on black holes at the moment from the CERN accelerators, and so watch this space, but don't get near a black hole, whatever happens. A few items about it. The diameter of this galaxy, our own Milky Way, is somewhere in the region of 100 to 150 light years across. pretty enormous. And an even more remarkable figure is that there are something like 180 to 400 billion stars in our own galaxy. And if you've not done it and you have a reasonable pair of binoculars and it's a nice warm night and you've got good clear viewing in the summer, lie on a lounger, look at the Milky Way with a pair of binoculars and you'll be absolutely amazed at the number of stars you can see in focus. And that is what we're seeing here, but in a different format. Another, I think this one's called the Pinwheel Galaxy. It's all got different names, particularly some of the more spectacular ones are given real live names as well as a huge number. This one, kind of, you can see it going round in a spiral like this, disappearing to the centre like that. Two other galaxies. These are the, just to give you numbers, UGC 1813 and UGC 1810. They're separated only by a fairly short distance of 100,000 light years. Hubble can catch this. You can actually see how flat the galaxies are spinning, and here's this one is almost on its side. They collided, they separated, and they collided with the smaller one is supposed to have collided with this at some times, and it's exactly the same as our own Milky Way galaxy. That will eventually collide with the Andromeda galaxy, but we've got plenty of time. It's somewhere about 4.5 billion years before the two galaxies collide there. Rather unusual pictures here. These two galaxies and really enormous things. It's believed that this one actually passed through this galaxy, and I don't quite know how it's done it or the details behind it, but ask an astronomer and you'll get 2 or 3 hours explanation, something like that. Rather pretty. You can see the stars developing here. And this is an artist's view of it's a Hubble series of photographs, so it's quite realistic in all the background and everything, but it's showing how a star can come in and spiral round and round and into the black hole. We have not got photographs of black holes yet or anything like that, but it's an artist's impression, which gives you a fairly clear view of this is going to take part in millions and millions of light years. And here we have a very special photograph, we'll come back to it, but it's showing some very, very deep views here. And we're going into the billions of light years away. And specifically, we see these orange and red areas that we're going to look at and explain towards the end of what Hubble is actually doing. Light bends, and you can see the effects down here, but it's something quite phenomenal. All these galaxies, thousands of them. This is a huge nebula cloud. It was a star that exploded. In fact, it's one of the smallest nebulae going. It's only about 1.5 light years across, that kind of order. And it's managed to be kept into this weird shape by the fact that some stars fairly close and their gravitational field are keeping it all compressed like that. So it's a big globular nebula. And here we have one of the most famous ones. It's called the Eagle Nebula. It was taken in 2009, and that's when it was released by NASA, this image. It's called the Pillars of Creation, masses of gas and dust. And the odd thing about it is, just to give you an idea of the size, it's 6,500 light years away from us. And these pillars, the 3 pillars here, are about 10 light years high. So they're astronomical, these figures, absolutely huge. And if you've got a good pair of binoculars and a steady hand, you might be able to see that one. It is one that's visible to the human eye. This one's the Veil Nebula. Just gives you an idea, some of the pretty colours you can get using all the different modes of photography with it's 8,000 light years away, and it represents a very violent death of a star, which exploded. All the dust and muck came floating out, and this is the kind of thing that's 8,000 light years away in space. This, I said, you remember the Einstein Telescope, that rather odd-shaped one. It worked in the X-ray spectrums, the very much higher frequency spectrums, and it discovered this. Nobody's seen it with ground observation or anything like that. And Hubble managed to pick it out because they knew it was there from the previous Einstein Telescope. And it's got a very interesting history. It was first seen it started off 2000, it was in AD 300 when St. Paul's Basilica was being built. And there was a very good solar eclipse, I'll get it right, apologies. The eclipse was very, very good. And in the southern skies beneath the eclipse, they actually saw a very large, bright light. And this was a planet, or star, which had actually exploded 1,700 years ago. And this is what's left of it now. And it won't be around for long. It'll certainly be around while we're looking at it. But if we take these nodules at the end, these knots, they're traveling away at a phenomenal speed. And the speed is something like 2 million miles per hour. So it just gives you a kind of feel of how fast it's moving. It's now 200,000 light years away. So again, a remarkable discovery. And they were able to trace its history back by measurements, spectrographic measurements of looking at one area of it. Hubble looked at it, I think it was over probably about 10 years. They looked at it and took the measurements and then compared it with measurements another 5 years later and another 5 years later. They got these different measurements and they could tell the speed at which it was disappearing and expanding. Oh, sorry, I've just jumped up. There we are. This is the one that's in Orion. Orion, under the belt of Orion, and it's called the Horsehead Nebula. And you can see there's a definite stretch your imagination a bit, but you can see this Horsehead Nebula here. It's 1,300 odd light years away. It's about 3.5 light years across. And it's one of the early things, if you're an amateur observer from the Earth with your telescope, then this is one of the things. You're doing pretty well if you manage to pick this out with anything up to a 4-inch, a fairly small telescope. You can just about pick this out. But if we look at it in more of the infrared, and this is quite a major area that Hubble's working in, you can see it's perhaps a bit more like a horse's head here, but you can see a definite different shape, more information coming out of it, very red backgrounds and everything. And sorry, if we just go back to the original one, you can actually see these kind of cutouts here and the basic shape in the actual infrared. There's a photograph altogether. And scientists and observers can look at this and get a lot of information about what's inside these huge dust clouds that have come from the exploding stars. This one's called the Crab Nebula. If you look at it, you can see that it's got a basic format of a crab. But let's look at it from the 3 different cameras. The images were released of the infrared cameras, looking at it, the ultraviolet, the much higher frequency colours, they were able to attribute something like that. And then the mid-range frequencies of visible light, the greens, yellows, and here we have all these spider things. If you take any bits of them, this bit here, you can see it's there in the composite picture. This section here, you can see around there, and obviously the mid-range colours all around there, like that. So it's quite a remarkable photograph to see how it's been built up on the different cameras and taking the different filtered images. Here's the Butterfly Nebula, a rather beautiful one. We've already seen it tonight from Calgary. Maria had a picture of it in her calendar. And there it is, obviously given the name as Butterfly because it looks like it. Inside there is an absolutely white, it's 4,800 light years away, and it's got a central red giant star in it. And that's pretty cool. It's only running at 22,000 degrees centigrade, enormous temperature, but it's cool, and that gives it red. And you've got all this nebula, which is dust and particles coming off it and gases. And here we have, looking at it a bit more in the blue spectrum. Just a few photographs of different areas of nebula. They're quite incredible. You've had to put little bits of artificial colouring in to emphasise it, but that is exactly what's there in the gaseous clouds. Very, very deep space colours coming in at red. Perhaps one of the most spectacular pictures that was released by NASA. And here you can see the definite effects of the spider, which holds the secondary mirror in position. It's got to have support arms, the secondary mirror, no matter how thin you make them. You've got to get them to a certain strength, obviously. But those support arms do cut out a certain amount of the light coming into the Hubble primary lens. And this is the effects you get. You get it on all space telescopes. You can get rid of it by special corrective measures, but most astronomers really like to see it. I do. I think it makes them very pretty indeed. More nebulae. They're just quite remarkable, these. Other ones. And really, now we're getting to the end of Hubble and its usefulness. This is the extreme deep sky field. Its pictures were taken over, well, the 2 million seconds worth of exposures here, not all done at once. It was done 2002, 2003, and 2009. The pictures were taken, and as I say, it comes out to about 23 days worth of exposure. This is Hubble. It's looking as far as it can possibly go. We can't go any further. Hubble's got its limitations, but you can see there's a predominant red on it. And the red comes from the fact that as light comes from stars, and some of these stars are 13.2 billion light years away, massive distances, really the extreme views that we can get. As the light comes past these stars, from the galaxies and stars coming from such massive distances, they come past other galaxies, and there is an interaction which actually bends the light and it slows it down. And as the light slows down, obviously it's moving from the blues, the greens, it moves more towards the red end of the spectrum. And this is why we're seeing so much red in these very distant pictures here. And as I say, Hubble's getting very near to the limits of what it can do. And let's just take a speck here. Try and find a little red one, something like that. And we look at that and we say, okay, Hubble, well, we've got that in view, let's blow it up. And you blow it up and you end up with something like that. It's a pixelated picture. You cannot get any more information out from Hubble, and that's all it is. So there we are. Hubble's really done its job. It's still doing a lot of work, and it's kind of limits, we get into the limit of it. 13 billion light years away, and that's as far as it's observing. It had quite a few service missions to it, and well, all kinds. The first one was the CoStar. That was the big one. We saw the second launch, and that was the big camera that went in. Another 4 years later, new cameras went in, reaction wheels, field guidance sensors, new computers a little bit later, and in March 2002, new gyroscopes. lots of new equipment, more advanced equipment was put in. And then in 2003, we had that dreadful accident where Columbia, the space shuttle, was coming back into Earth's atmosphere through the ionosphere, and it was, obviously, it's got the heat shield on from all the tiles on it, and some of the tiles had broken off during, I think it was during the launch, and unfortunately, it allowed the heat to get in, and it broke up Columbia itself and killed all the astronauts on it. And from that, NASA said, that's it, no more actual work. Hubble's not going to be serviced anymore. We're shutting down the missions using the shuttle. It was a disaster for the scientific world, who were getting used to Hubble and asking for all these different pictures. There's so much pressure put on NASA that eventually, we're talking about 6 years later, they allowed one more service mission to go out. And that put all kinds of new cameras, wide field cameras, gyroscopes, batteries, you name it. And also something called a soft capture mechanism, which we'll look at in a second. That's it, no more. The astronauts who went up on it basically shook hands with it and said goodbye, and they left it. And it's really expected that there's going to be 10 to 15 years of life left in Hubble. And with a bit of luck, it might get up to the year 2040. Here we are, still working away. But you've got something like 10.5 tons, the size of a bus, and that eventually is losing, it's not being jacked up in orbit anymore, there's nothing that can send it higher. So its orbit is very gradually decreasing, and without doubt, like all satellites, it will enter the Earth's atmosphere and burn up and crash. Now, something at 10 plus tons isn't going to be the kind of thing that you want landing in New York, Toronto, Calgary, or even Plympton. It's just an enormous risk. So what they've decided to do is they put this soft capture beam, here it is, it's the last thing that's put on Hubble, and they're going to have a robotic service mission come up. It will grab a hold of Hubble, and under huge control from NASA, it'll start to bring Hubble down, down and down at a correct descent rate and on the correct parameters, so that it more than likely ends up in the vast Pacific Ocean and does no damage there. So basically, that's what's going to happen to Hubble without any doubt. Very sad, but it has done a phenomenal job. And what's it going to be replaced with? Here we have something that looks like it's out of Star Wars. It's called the James Webb Telescope in honor of a later American. And this mirror now, instead of being 2.4 meters diameter, is 6.7 meters diameter. So its resolution goes up by at least 100 times. The mirrors are assembled, self-assembled in space, and you'll see why in a second. You can't really have any service missions. It's a one-off shot, this. Light comes in, hits this mirror, off the primary mirror, onto the secondary mirror, which is supported here, down through the large hole in the aperture in the primary mirror, onto lots of cameras stuck around the back of it here. And masses of equipment here. It's a long, long way out in space. Lots of solar panels on the transmitting equipment. But that is going out, and as I say, there's no servicing going to be due on it. It's due to go out. It's being delayed, obviously, by the COVID crisis, and I think it was going to go later on this year, and it's planned, hopefully, for next year to be launched. Where is it going? Well, let's just have a look at this area here, and to get this picture on, I'm afraid I had to squash it. Here's Earth, here's Hubble, and Hubble is 570 kilometers up. The moon is just about 6 or 7 times further away than Hubble, again squashed up. But if we go out and out and out and out, 1.5 million kilometers, we come up to an area called the Lagrange 2 area of space. It's extremely cold. The gravitational effects from Earth are pretty minimal. And here we have the Webb telescope is sent out to there. It's working in pretty near absolute zero conditions, and absolute zero is minus 273.15 degrees centigrade, a very, very low temperature. You can't go any lower than that. And at that point, all atomic vibrations, electronic motions, and interference virtually stops. And so it's in this very cool area out here, collecting information which is primarily beyond what Hubble stopped at. And that information is in the infrared section of the spectrum. It will do color pictures, but basically any information that's coming from deep outer space is coming through on the longer wavelengths, more like the infrared. It'll transmit the data back to Earth, and it'll be picked up by telescopes, well, not telescopes, receiving stations, a bit like Jodrell Bank and Goonhilly Downs, massive parabolic receivers with an aerial system right in the center of the reception of the parabolic focus. And those aerials are down pretty near to absolute zero, about 250 degrees centigrade minus. And the idea of this is that it stops all the hiss and the buzz of electronic noise coming in, and the information it picks up is true information in that case. So that's the next generation. It's coming up. And basically, we don't know quite when it's going to be launched, but watch this space. It then leaves me with the thoughts of what would these gentlemen have thought of it? Galileo Galilei, the scientific genius of the 17th century, obviously. What would he have thought of this, and how would he have used the information? Edwin Hubble, obviously regarded as the leading observational cosmologist of the 20th century. And then finally, James Webb. He's not with us anymore, but he was the American executive who ran NASA between throughout the 60s, looking at the Mercury and Apollo flights. And the new telescope is named in honor after him. And so effectively, turn around and say, well, is there a final thought to it? Is there a finite end to our universe? I don't know. It worries me a bit. Can there be an end? People say it just carries on. I do not know. We went from a big bang. Somebody last night was telling me that there's theories that we've had more than one big bang, and that's contributing to the universe ever expanding. But one thing I do know is that whilst that's going on, a lot of research this side, the End Polio Now project, we'll crack it. We're nearly there. We're down to a few live cases, just about a dozen in Afghanistan, northern Pakistan. Most of Africa's been cleared, I believe, but I do hear there's problems there as well. And so, with luck, we will get to the end polio now and eradicate that dreadful disease, just as we did smallpox. And that's where we'll pull in, and I make apologies for dragging on so long. It's gone for just about an hour now, but hopefully you've enjoyed it.
Thank you, Tony, for that. Time has gone a bit, but we've got time for a couple of very quick questions. And I know Shannon put a question in the chat earlier on. So Shannon, do you want to ask your question first of all?
Yes, thank you, President Darren. Thank you, Mr. Bell. It was really a wonderful presentation. I'm very excited to have seen it. I'm glad I was here. My question was, you mentioned the baseline temperature inside the Hubble telescope, and I was wondering what creates heat inside the telescope that needs to be maintained.
Right. Well, there's the motors. They pick up heat during the day, obviously, when it's in the space and not looking at the sun, but off on that direction. I'm not absolutely sure. The motors are working quite regularly, obviously stabilizing the telescope, and they will give out a fair amount of heat. The insulation on it is massive. The aluminum reflectors to stop incoming heat. And I think most of it is self-generated from the electronics. That is a stable temperature, but I'm not absolutely certain. I'll have to try and find the details of that one, I'm afraid, Shannon.
Okay, thank you very much.
That's fine.
Okay. Any other questions? David Roberts. You'd have to unmute yourself. David, you're on mute.
Thank you. Incredible talk. Thank you. The aperture door, is that controlled by the Hubble spacecraft, Hubble telescope itself, or is that because you say it closes when it's every so often?
I believe it's certainly automatic closure when it's getting anywhere towards the sun, but I don't think Hubble's going through dust and debris, so whether it's kept open permanently, it isn't the aperture of a camera. Like a camera opens for a certain second, then it shuts. That is not the control feature. It certainly opens for the period that they're going to be observing, and then presumably they shut it to try and keep the heat stable and everything when it goes into cooler.
And
orbit.
One other very quick question was, the tracking satellites, I assume they travel more or less at the same speed as Hubble.
Yes, I think they're more in geostationary orbit.
But they got so many.
There's certainly more than one or two. I did read it, but I've forgotten the numbers. But
thank you very much.
Communication. That's here. Thanks, David.
Fascinating.
Okay, any more questions? Maria, is that your hand up for a question?
Just no, it's more like a comment. It's an amazing presentation. I am fascinated by the cosmos, and I just want to make a comment about the Canadarm.
If you very quick,
the Canadian logo. So proud Canadians that we are. We want to make notice of that. That the Canadarm is one of the arms that helped with the servicing of all kinds of other things in space. So there, I wanted to mention that.
Thank you, Maria.
Very interesting. Thanks very much, Marie. And hopefully we can get an email for you sometime and have a chat about Canada and Calgary and Edmonton.
Absolutely.
Well, we spent a year as a family.
Yes, absolutely. We would love that.
Okay, folks. I'm afraid time has rode on a bit. So, Sarah, could I ask you to give the vote of thanks, please?
Yes. Can you hear me, Darren? Yeah.
Yep.
Coming through. Okay. Tony, that was just amazing. Thank you so much. You've managed, certainly for someone like myself, not a scientist, you've managed to somehow make so much of it very clear, and the scale of everything and the enormity of the tasks, and also the history and the people involved. There was so much packed in there, and I'm just in awe. I don't know how else to put it like that, really. But I just wanted to for explaining so much and your familiarity with all the figures, and you can somehow explain the scale of it all, because I think that's the astonishing thing, isn't it? It's just so hugely big. And then when it gets to be really, really large, it sort of looks like a bowl of frog spawn. And I just don't know quite how that happens, but that's fine. So could we all show our appreciation, please, to Tony? I'm sure you don't want to say.
Well, thank you again, Tony.
Thank you very much indeed. It's been a delight to talk to you.
Well, it's been great having you with us.
My apologies.
Okay, folks.
My apologies.